Now that we've talked about exponents and powers, both positive and negative exponents, we're going to start performing some operations with these expressions that contain exponents. We're going to talk about multiplying and dividing something we call monomials. And a monomial is simply a number, a variable, or a product of numbers and or variables. What? Well, a monomial is simply just a single term. There's no addition or subtraction involved. So in the left in the yellow box, I've got examples of monomials. A monomial is just a single number, a single variable, or when we multiply numbers and variables together. So 5 is a monomial, a single number. X is a single variable. 13 to the 7th power is a product of numbers, 13 7 times. X times Y times Z is a product of variables. That is a monomial. 14Z is a product of a number and a variable. 6 times 12, a product of numbers. And 34RT to the 4th power is a product of numbers and variables. Those are all examples of monomials. Again, not an exhaustive list, but whenever you have a number, just a variable, or you're multiplying numbers and variables together, you've got a monomial. In the blue box, I've got examples of things that are not monomials. 3 minus g, there's subtraction there. That is not a monomial. 7 plus 29, not a monomial as written. If we were to actually add those together and get 36, that would become a monomial, but as it's written, it is not a monomial. X plus 7, not a monomial. You're adding two things together. 3z squared minus z plus y, not a monomial. There's addition or subtraction there. 18 minus 9 plus n, not a monomial. There's addition or subtraction. So long story short, whenever you see addition or subtraction, you do not have a monomial. So how do we multiply these monomials together? Well, if you're multiplying powers with the same base, we're going to use something called the product of powers property, which is kind of fun to say, product of powers property. And that says that if you have the same base and you're multiplying things together, you just have to add their exponents together. So why does that work? I've got some examples right here. If we look at this, 5 to the 3rd power times 5 to the 4th power, we actually, if we expand this into what this actually means, 5 to the 3rd power is 5 times 5 times 5. And I'm multiplying that by 5 times 5 times 5 times 5, or 5 to the 4th power. Well, the commutative property, or sorry, the associative property says I can just remove these parentheses and just write it as 5 times 5 times 5 times 5 times 5 times 5 times 5. Well, that's just 7 5s that I'm multiplying together. So I can just write that as 5 to the 7th power, which is 3 plus 4. I've got 3 5s multiplied by 4 5s. That gives me a total of 7 5s. So that's the product of powers property. Whenever you have the same base, all you have to do is add the exponents together to simplify that expression. So a few more examples here. I've got g to the 8th power times g to the 4th power. Well, I have 8 g's multiplied by 4 g's. That's a total of 12 g's that are being multiplied. So that would be g to the 12th power, according to the product of powers property. Here I've got a positive and a negative exponent. 6 to the 8th power times 6 to the negative 3rd power. That would be 6 to the 8 plus negative 3 power, which is 6 to the 5th power. Up here I have 12 times 12 to the 4th power, and this is like 12 to the 1st power plus 12, or times 12 to the 4th power. So there are 5 12s that are being multiplied together. So that's 12 to the 5th power. And then here I have t to the negative 5th power times t to the 3rd power. So I would add those exponents together. Negative 5 plus 3 is negative 2. So I get t to the negative 2nd power, or again, remember, that's the reciprocal of its positive power, 1 over t squared. So the product of powers property says simply add the exponents together to simplify the expression. So let's find each product, and we're going to express using positive exponents. We're not going to actually evaluate the power. We're just going to simplify it to write it with a single exponent. So 5 to the second power times 5 to the third power, that would be the same as 5 to the 2 plus 3 power, which is 5 to the fifth power. I've got 5 5s there. Next, 12 to the third power times 12 to the negative second power. I'm actually going to have some 12s canceling each other out here, because you can think of that negative 2 as 1 over 12 to the second power. So these will actually cancel each other out, and I'll get 12 to the first power, or just 12. And then the next one, x to the negative 6 power times x squared. That would be like x to the negative 6 plus 2 power, which is x to the negative fourth power. And since we need to write this with a positive exponent, I'm going to find the reciprocal, 1 over x to the fourth power. And then lastly, here we've got a lot going on in these monomials. Again, I'm going to use the commutative property to rearrange these a little bit. I'm going to put my numbers together, and I'm going to put my n's together here. 10 times 5 is 50. And the product of powers property says that n to the 7th times n squared is going to be n to the 9th power. So this is 50n to the 9th power. So when you're multiplying expressions that contain a lot of parts, just go ahead and use the commutative property. Since we're talking about multiplication, put the numbers together, put the variables together, and then we can simplify from there. So how do you divide powers? Well, the quotient of powers property says that when you're dividing powers with the same base, we're going to subtract the exponents, because there's actually some canceling going on. Some of these are in the numerator, some are in the denominator. So again, I've kind of written this out longhand so you can see what's happening. 5 to the 6th power divided by 5 squared. So I've got 6 5s in the numerator here, 5 times 5 times 5 times 5 times 5 times 5. And 2 5s in the denominator. That's how I'm going to write that division in fraction form. And then actually 2 of these pairs of 5s are going to cancel each other out, which leaves me just 4 5s in the numerator left. So that's 5 to the 4th power, or just 6 minus 2. So the quotient of powers property says I can subtract the exponents to simplify the expression. Another example that I have here, 8 to the 3rd power divided by 8 to the 5th power. That's 8 to the 3 minus 5 power, or 8 to the negative 2nd power, which is 1 over 8 squared, if we wanted to write that with a positive exponent. Next one, m to the 14th power divided by m to the 3rd power is just going to be m to the 14 minus 3 power, or m to the 11th power. And then lastly, x to the 6th power divided by x to the 10th power is going to be x to the 6 minus 10 power, or x to the negative 4th power. And again, if I want to write that with a positive exponent, that's 1 over x to the 4th power. So product of powers property, quotient of powers property. One you're adding exponents, one you are subtracting exponents. So let's find these quotients here using the quotient of powers property. 3 to the 9th power divided by 3 squared, this is going to be 3 to the 9 minus 2 power, which is just 3 to the 7th power, and I'm not going to evaluate that. I'm just going to write that as a power. B to the 7th power divided by b to the 6th power, that's going to be b to the 7 minus 6 power, or b to the 1st power, or just b. 4 to the 5th power divided by 4 to the negative 2nd power, that would be 4 to the 5 minus negative 2 power, which is 4 to the 7th power. Actually, 5 minus a negative 2 is like 5 plus 2, and that's 4 to the 7th power. And then s to the negative 4th power divided by s to the 1st power, that's like s to the negative 4 minus 1 power, which gives me s to the negative 5th power, or 1 over s to the positive 5th power. Either one of those is equivalent. So dividing and multiplying monomials, product of powers property, quotient of powers property.